This is GMAX 41. You are welcome to our ordinary differential equation class. In this video, we now turn our attention to the homogeneous first order differential equation, having been done with our separable variable equation. In this video, we are going to see how we can identify the homogeneous first order differential equation and of course how to solve it using the transformation here and its derivative. Now first, how do you identify a homogeneous equation? Now you look at it generally. A homogeneous first order differential equation is given, as you see here on the board, there is mx, y dx plus nx, y dy equal to 0. Please take note that this plus can also be minus. Now, how can you identify that this equation is actually homogeneous? Number one, either in this function n, you will see where the variable x and y are added or subtracted. Or in this function n, you will see where x and y are added or subtracted. Or in the two functions m and n, you will notice that the variable x and y are combined by addition or subtraction. That is one thing you should note. However, it is not absolute reason to say that this equation is a homogeneous equation. Now, all in all, how can you now determine that this is a homogeneous first order differential equation? Now you listen to this, okay? The degree in m and n must be equal. The m term is bearing dx, the n term is bearing dy. It therefore means that the power of the variables altogether you have in this dx part, which is your function m, and the power of what you have in this dy part, which is the function n, they must be what? Equal. So if the degree in this dx part, that is the function m part, is 2, the degree here will also be what? 2. If the degree here is 3, the degree here will also be what? 3. That is the absolute test for what? For homogeneity of a first order differential equation. Does that make sense? Now, how do we solve this problem? To solve it, we use this transformation given by equation 1. You're going to call y to be ux. That is, y is equal to ux, where u is a variable, of course. Is that okay? And then we have to differentiate this equation 1 with respect to x. So you're going to differentiate this y with respect to x, you get dy dx, which is y prime, and then you differentiate ux. This is u times x. To differentiate it, you're going to use product rule, you know that, right? So I'm going to keep x constant, you look at it, differentiate u with respect to x, you get du dx. Is that okay? Then plus this time around, keep u constant, differentiate x with respect to x, which will give us what? 1. Now, what is the essence of this transformation and its derivative? It's pretty simple, you know. Once you define a transformation in differential equation, all you need to do is substitute that transformation into the equation and its derivative. The essence is to replace y with that transformation and also replace dy dx with the derivative of that transformation. Once you apply equation 1 and 2 into the homogeneous first order differential equation, it is going to reduce it to a separable variable, SVE. A separable variable equation. And once it reduces it to that separable variable equation, what do? You now use the knowledge of our separable variable equation to solve. Separate the variables and then integrate. At the end of everything, remember that your result must be in terms of x and y. So in your final result, wherever you see u, you have to replace that u with what? Y over x. Because you know that from here, u will be equal to y over x. And that's just your result. Now in the next video, we're going to see how we can test, okay, to find out that this equation is a homogeneous equation. Then we can start talking about how to solve them. Now we have this proof on the board, okay? We have to prove that this differential equation x squared y plus y cubed, or close bracket dy equal to open bracket yx squared minus x cubed close bracket dx is homogeneous. And then what is the degree of that differential equation? Honestly, by observing this, one can straightforwardly tell that this is a homogeneous equation of degree 3. I'm going to show you the test procedure. From the test procedure, I'll then tell you what you can do to quickly identify that this is homogeneous and state the degree without actually going through the main test procedure. Now let us apply the test procedure. What do we do? We're going to select a constant. I will use lambda as a constant, okay? Then make sure that you use the lambda to multiply each of the variables in the given differential equation. Then you know something, whatever power that the variable is bearing, the constant you're using to multiply that variable will also bear that power. So let us do that and see. Selecting lambda as my constant. So I'm going to use lambda to multiply x squared here. It's going to be lambda times x, everything squared. Then times, you have your y here. Use lambda to multiply that y. Remember that this will be raised to power 1 because this y here is raised to power 1. Plus, come to this term, use lambda to multiply the y. Right, to be raised to power 3. Then this is our dy term, okay? So this is called n. Alright, it will be equal to, come to this, use lambda to multiply the y, that is y raised to power 1, so everything will be raised to power 1 there, times x. Use lambda to multiply the x is squared, okay, then minus, come to this term, lambda times the x. That x there is carrying power 3, so you're going to put power 3 there. You can see that, right? So this is the first step, dx. So let us now simplify out the lambda and see what we're going to get. You know that this is lambda squared. Lambda squared times x squared times lambda raised to power 1 times y raised to power 1 plus, come to this term, lambda cubed y cubed. So we're going to be bearing this dy. Then we'll move on to this part. Open up the bracket there. We get lambda raised to power 1, y raised to power 1 times this will give us lambda squared, x squared minus lambda cubed, x cubed, then dx. Now let us come to this part and then you take note that you have a lambda squared here times lambda raised to power 1. So you're using this is law. When you're multiplying the same base, you add the powers. So I'll pick the lambda there. 2 plus 1, okay? 2 plus 1 will give us 3. Then you notice that this is x squared y. So have x squared y. Plus, come to this term, you have lambda cubed as well. Let's have our y cubed there. Good. Everything is bearing dy. Then we'll move on to the dx part. You notice that this is lambda raised to power 1 times lambda square. The same base, they multiply, and so you pick one of the bases, lambda, add the powers, 1 plus 2, it's going to give us 3 there. Then this is y raised to power 1 times x squared, which will give us yx squared, or x squared y. Good. Minus, come to this part, you have your lambda cubed, then your x cubed. Good. This is the x. Now what did you notice here? Did you notice that this term here and this term here, you have plus in between them? Lambda cube is common, isn't it? So you factorize the lambda cube out. So you have x squared y plus y cubed and then dy. Equal to this part again, this part, you have negative between them. Lambda cube is common. Factorize it out. So you're going to have x squared y minus x cubed, then dx. Alright, so we are done, okay? Did you notice that the dy part has lambda cube, okay? As a constant, the degree there is degree 3. You can see power 3 here. And then the dx term also, you notice you have lambda cube. The degree there is what? 3. So this simply means that this differential equation is a homogeneous first order differential equation of degree 3. We've done the test. Of course, this is quite like just a formality. One can look at this clearly and then state that this is homogeneous of degree 3. Let me quickly do that, okay? This is x squared times y. So what do? Add their powers. Yes, the bases are not the same, no problem. We know that the bases are not the same. But if you want to go straight by the observation principle, you're going to violate that rule of indices that say that the bases must be the same before you add the powers if you're multiplying the base. You see here that actually what we are adding is not these powers of this base. It's power of something. The lambda, there is an answer. Since you're not introducing lambda directly, you just work on 8. You have x squared y raised to power 1. So add up the powers, you have 2 plus 1, giving us 3. So this term here is power 3. This one is also power 3. So power 3 is common to these two terms added. Take note of that. Then come here, do same. This is y raised to power 1, this x raised to power 2. Add the powers. You have 1 plus 2, which is 3. This term here is also power 3. So this part and this part, power 3 is common to them. So since you have degree of 3 here, degree of 3 here, it means that this is a homogeneous equation of degree 3. Next video, we're now going to start solving questions on homogeneous equation. We now have this question on the board to solve, okay? X squared minus y squared dy minus 2xy dx equal to 0. Now observe this, that this is a homogeneous equation of degree 2. You can see clearly here, the common power there is 2, so the dy term is degree 2. If you come to this part, this is x raised to power 1 times y raised to power 1. Add the powers, you are going to get 2. Is that also? So the dx term is also degree 2. Take note, you have no business with this constant in order to verify whether this is degree 2 or not. So the dy term is degree 2, the dx term is degree 2, so this is a homogeneous differential equation of degree 2. Now let us make dy dx subject of formula first. To do that, we're going to write dy over dx, this dy over this dx. Since you are dividing here by this dx term, then you divide minus 2xy by this x squared minus y squared. Is that okay? But let's assume that this has crossed over to the right hand side first. So it crosses over to the right hand side, this will become positive there, is that also? So you're going to have equal to 2xy all over x squared minus what? Y squared. You take note that this dy over dx is the same as what? Y prime, don't forget. Okay? So what we do from here, we can now apply our transformation. Recall that to solve your homogeneous differential equation, you apply what? This transformation, and then you have to differentiate it to have y prime equal to differentiate this, use product rule, keep u constant, differentiate x. You get 1 times u, which is u plus. This time around, keep x constant, differentiate u, you have u prime. This is equation 2. So what do we do from here? Substitute for y and then y prime. You know that y prime is the y dx. So go to this differential equation and substitute there. Okay, if you are substituting, it implies that your dy dx will now become u plus x u prime equal to, this will give us 2x. In place of this y, you fix u times x divided by, this will give us x squared minus, in place of this u, we're going to substitute ux, which each of them will be squared. You know that, right? Ux all squared. Then you get x squared u squared, or u squared x squared. Now we are going to have u plus x u prime equal to 2u x squared. X times x will give us x squared, okay? Then all over, look at the denominator, x squared is common. So you factorize the x squared from here, you'll be left with 1 minus u squared, right? To factorize this term you brought out, which is common to two of them, use it to divide each of them. So it will be x squared divided by x. You get 1, then x squared u squared divided by this positive x, you'll be left with what? U squared. And now you would agree with me that the x squared term will cancel out. Then we would have x times u prime equal to, let's take this u to the right hand side. We'll have 2u all over 1 minus u squared, then minus the u that we crossed over. We can find LCM of the right hand side, okay? We can find LCM of the right hand side. Then this can be written as x times du dx, because u prime is du dx equal to, how do you work out the LCM of this? This is a whole number, then this is a fraction, so it's going to be 2u the numerator, then minus denominator times this whole number. We've done that before, right? So if you have minus u times 1, you get minus u. Then minus u times minus u squared will give us plus u cubed. Everything all over 1 minus what? U squared. We are moving on, so that our x du over dx will now give us u plus u cubed all over 1 minus u squared. This is a separable variable equation, okay? You want to see that clearly, cross multiply and you see x times du is equal to u plus u cubed all over 1 minus u squared dx. Now this whole term is a u term multiplied by the differential coefficient dx. and then this is an x term multiplied by the differential coefficient du, so you can separate this. This is your separable variable equation. Let's separate that quickly and see. To separate, this u term will come over here, this x will go there. If the u term is coming as 1 over u plus u cubed all over 1 minus u squared. Alright? Then du equal to this x term will come over here as 1 over x dx. Do you know that mathematically, look at this, this is an inverse of this term, so this denominator will go upward mathematically, division of fraction. So we're going to have 1 minus u squared all over u plus u cubed du equal to 1 over x dx. We've separated these variables, is that okay? So at this point we now need to do what? Integrate. So we're going to take a break. When we come back, we can now integrate this term. Here we'll be solving partial fraction because the denominator can be factorized into u plus 1 plus u squared, which means you have to solve this integration by partial fraction. There is no problem about that. So be thinking about it while we take a break. We'll come back to solve this problem. Alright, so we're going to solve this integration problem. Recall that before the break, we obtained this as the variable separable form of these homogeneous equations. So to integrate, look at this term, we're going to solve this integration by partial fraction. It's the same as 1 minus u squared all over, the denominator is factorizable to this term. Is that clear? Then du, which is integral of this, it's pretty simple, so we can just get it. It's a standard integral, ln x. I won't put plus c because I'm yet to complete my integration. Now this part can be solved by partial fraction. Now let's formulate the partial fraction to this. You notice that this will be integral corresponding to this linear factor as denominator. We're going to get a over that denominator, then plus this is a non-factorizable quadratic denominator, and the partial fraction will be bu plus c all over 1 plus u squared. Alright, then du equal to ln x. This is just like the term which we used to have ax plus b. Now I've used a before, is that okay? So that's why I used bu plus c. Here the variable is u, not x. And that's why it's going to be bu plus c. So we're now going to solve this partial fraction. For this term, we would use the denominator closing format. In the denominator closing, look at this. The denominator here is u. If I select u to be equal to 0, then this denominator of a will be 0. That will give me room to calculate a. Is that okay? So I would say let u be equal to 0. If u is equal to 0, the denominator of this a will be 0. Then it will help me to calculate a. And how do I do that? I'll go back to this term. Take note that in the partial fraction, this whole term is equivalent to this. So you can write it out as you see what I'm going to do. Close this u, which is 0 from here already. Then what is now left is 1 minus u squared all over 1 plus u squared. Substitute 0 for u there. And if you do that, you have 1 minus 0 all over 1 plus 0, which will give you 1 over 1. So the value of a there is what? 1. Then let's proceed. We'll come to this part to obtain either b or c. I'm going to look at it and see if I decide that u should also be equal to 0, for example, in the numerator, then this b will disappear. You notice something that we're using the denominator closing method. If you select a value from the numerator, you are not going to close anything. There you use the numerator free variable format. Is that okay? So if I assume u to be 0 from the numerator, based on what I'm saying, b will be 0, a and b, or a and c will be left. So you substitute for that u which is selected and then solve for what is left. Let's try that and see. Again, let u be equal to 0. Okay, now this is what I saw that made me decide that u should be equal to 0. It implies that you are not closing anything. You are not closing anything. So you come to this term, which is equal to this term, substitute 0 for u. That will be 1 minus 0 squared all over 0 bracket 1 plus 0 squared. This will be equal to this. Our a already is what? 1 all over 0. Then plus we come to this. This is b times 0 plus c, which you don't know, all over 1 plus 0 squared. Okay, let us see what we're going to get from that. This time will give us 1 over 0 1 over 0, which normally is supposed to be a concept of infinity or whatever. But let's see something come over here, still equal to 1 over 0. And then this will give us b times 0 is 0. 0 plus c will give us c all over 1. Now, to make c subject to the formula, this will go over here. 1 over 0 minus 1 over 0 will give us 0. Then c is equal to what? 0. Now that we've obtained the value of a and c, at this point we can select any value in this world for u again and then get the value of what? B. I'm going to use u to be equal to 1. Let u be equal to 1. If u is equal to 1, take note I didn't select that 1 from any denominator. I did not. So in this case, it's still a free variable, so you substitute into this and solve for b. So in doing that, we're going to have, it implies that 1 minus 1 squared all over 1 bracket 1 minus 1 plus 1 squared. That is for this. Every term will be equal to this. So our a is 1 all over 1, then plus b times 1, then plus c, which is 0, divided by 1 plus u squared, which is 1 squared. If we solve out this, the numerator here will be 0 all over denominator here. And you know, 0 divided by any number is 0, so I can fix in 0 there. This is 1. Come over here. This is b plus 0, which is b divided by, this will give us 2. Now if we have this, can solve out this, 1 will come over here. You have minus 1 equal to b over 2. Therefore, b is equal to minus what? 2 by cross multiplying. So we have gotten the value of a, b, and what? C. Let's write them out here. A is equal to 1, b is equal to minus 2, and c is equal to 0. We'll take a break again. Once we come back, we'll substitute for a, b, and c, and then integrate this part. Now that we've solved this partial fraction and obtained the value of a, b, c, we can now substitute and then do our integration. A is 1 over u. Of course, du, you know that? And then plus b is minus 2. Now watch. If b is minus 2, that minus 2 will change this plus to minus. So let's just put minus 2u. And then c is 0 plus 0, no need of putting that. All over 1 plus u squared. Good. Then du equal to ln x. We're going to work this out quickly. Integral 1 over u du would give us ln u minus integral 2u all over 1 plus u squared. Remember, differentiate the denominator to see if you get a numerator. If you differentiate 1 plus u squared, you are going to get 2u. Is that not so? That u is what you have in the numerator, that is the 2u. Therefore, the integral of this term is ln of the denominator. We are done with the integration. That will now be equal to ln x plus what? Ln c. At this point, I've now introduced the constant of integration. Can apply law of logarithm here. Come over to this part. This is ln u over 1 plus u squared equal to ln cx. Take exponential of both sides. So you have u plus u over 1 plus u squared equal to cx. We can now return back the value of u. Recall from our transformation, y is equal to ux. So u is now going to be y over what? X. So we're going to substitute that. Let's see what we will get. In place of this u, I will put y over x all over 1 plus y squared over x squared. You know, the y squared over x squared, because of this u is squared. That will be equal to cx. The denominator can be simplified further using LCM. This is a whole number, this is a fraction. So it's the same as y over x all over x squared times 1 will give us x squared plus the numerator y squared, everything divided by x squared. Okay, so you see you have denominator fraction, you have numerator fraction. What is cx? Do you know that mathematically this can be written as y times x squared all over x bracket x squared plus y squared. Okay, check it out yourself. Mathematically, this x we cancel 1 from here, and if that happens, we'd have yx all over x squared plus y squared equal to cx. It's equal to cx. And again, do you know that mathematically you can divide through by x, because you have x here, then this would cancel out. And if that is the case, what would we have left? Watch, we're going to get y all over x squared plus y squared equal to c. So this is the solution, the simplified solution to this homogeneous differential equation. Or we can choose to write this as y equal to x squared plus y squared times c, whereby this c will come over here as denominator, y over c equal to x squared plus y squared. And you know that this is the same as 1 over c times y equal to x squared plus y squared. 1 over c is constant divided by constant, which will still give you constant. So this 1 over c can simply be written as c times y, which will give us cy equal to x squared plus what? Y squared. Therefore, you see that your result can still be divide both sides by y. You have x squared plus y squared all over y equal to what? C. And this is another simplified form of the result of this homogeneous differential equation. Let us now look at this second question. Okay, we have to solve the D.E x y prime equal to y plus x exponential minus y over x. Now to solve this, we can ideally rewrite it as x dy over the x equal to y plus x exponential minus y over x. And now if you look at this, suppose you cross multiply, so this whole term will be the dx part. Is that okay? Now you will notice first of all that you have a y and then x variable here added. So there is addition there, plus. Good. Now let us check the degree now and see if the dy term and dx term have the same degree. Now if this dx is being cross multiplied to go here, you will notice that this x dy, this x is raised to power 1, telling us that the dy part is degree 1. Then the dx part here, look at this y is raised to power 1, right? This x is raised to power 1. Look at this exponential minus y over x here. This y is also raised to power 1, this y is raised to power 1. Is that okay? And you know that all in all, like, if this is y raised to power 1 all over x raised to power 1, you can subtract the power, you have 0 at that part. So you'll be interested in this, that this is power 1, this is power 1. So that the degree is degree 1 in the dx part. In conclusion, dy term has degree 1, dx part has degree of what? 1. And so this is homogeneous equation of degree 1. To solve, what do we do? Let's our y be equal to ux as usual, and then we're going to differentiate to get y prime equal to u prime of x plus u. Is that not so? That's differentiate using product rule. We can now substitute into this equation. To do that, you know, we need to rewrite this as dy dx. Write it as dy dx, and then dy dx will be equal to y plus x exponential minus y over x, everything divided by x. You have to divide here by this x to make dy dx subject. So we substitute for this y prime using this. That's going to give us u prime of x plus u equal to, in place of this y, we're going to put ux plus x exponential minus ux all over x. Now substitute for this y here using ux. Then divided by the x term. Now look at what happens in this exponential of minus ux over x here. This x and this x will cancel out. And if they cancel out, you have exponential minus u. Is that not so? Good. Now look at this ux and this x exponential minus u. What is common there? You'll agree with me that x is common, so this becomes x open bracket u plus exponential minus u divided by this x. There is x term here, there is x term here. Once again, this x will cancel this x. Then take your u from this part to the other side. If that goes, you're going to have u prime. Okay, let's write that as du dx now. So x times du dx, x times du over dx is equal to u plus exponential minus u plus exponential minus u. This u will cross over to become minus u. And then you see that this is x du over dx equal to exponential minus u. This u and this u term will cancel, we know that, right? So they will go off. This is our separable variable equation. You want to see that? You can cross multiply. If you cross multiply, you have x du equal to exponential minus u dx. This is a separable variable equation, like I said. Okay, look at this. Let's quickly separate the variables. This u times this du differential coefficient, so we'll bring it here. Then this exponential minus u will come to its controlling differential coefficient. It's going to come as 1 all over exponential minus u du equal to this x will come over here as 1 over x dx. You separated. Now, do you know that this exponential minus u can still be written as exponential positive u du like this? Negative index law of indices. This exponential minus u will go up. Just like if someone gives you 1 over x raised to power minus 2, it's the same as x raised to power what? It's the same as x raised to power what? 2, this way. So that will now be equal to 1 over x dx, which will now be left to do what? Integrate. We're going to take a break. When we come back, we'll integrate this term to get our result. You're welcome from a short break. Before the break, we obtained exponential u du equal to 1 over x as the separable variable equation form of this homogeneous equation. Is that not so? So at this point now, we are going to integrate the term which you have on the board here. And fortunately enough, these are standard integrals. So obtaining the value is very, very simple. Integral of exponential u is going to give us exponential u. Is that okay? Equal to integral 1 over x is going to give us ln x, then plus what? C, the constant of integration. Take note that I did not introduce ln c, ln to that constant, because not all the terms here are bearing ln, okay? And at this point, you know that we have to substitute for u. Recall that the transformation we use is y equal to ux, so that u is equal to y over what? X. Does that make sense? So let us now substitute, and then we have exponential y over x equal to ln x plus c. This is our solution. We might still choose to play around the solution by doing further simplification. If I take ln of both sides, what's going to happen? The ln will remove this exponential sign. But before then, let me just underline this as part of our answer. Then I'll write or. Taking ln of both sides, the ln will remove this exponential, and you'll have y over x equal to ln of ln x plus what? C. Okay? And if you decide to cross multiply, you have y to the x ln x plus what? C. So this could still be an answer to this question. And that's how we solve this homogeneous equation. We have this third question on the board here. Obtain the IVP of the DE x squared y prime equal to y squared plus xy minus x squared. Y of 1 equal to 2. This IVP simply means initial value problem, okay? Once you see that thing, what does it mean? It simply means solve the given differential equation, obtain the general solution. You remember, all the solutions we've been obtaining since, they are general solutions because they contain the constant of integration c. Now, if we are given boundary conditions, these are called boundary conditions. This means the value of x is 1 and then y is 2. That's the meaning of this. Good. So you're going to use this boundary condition to obtain the constant of integration in that equation, so that the final solution you will now get to be called particular solution. Now let us do this and see. The question given to us is x squared. Of course, you know it's dy over dx. That is xy prime equal to y squared plus xy minus x squared. Please observe this and see that it is a homogeneous equation of degree 2. How did I know that? If you cross multiply the dx to go to this part, now you notice that the dy term is carrying x squared. So the dy term is of degree 2. Then if you look at this part, you see x and y being added, you know, just like we said. So you should be suspecting that it's also homogeneous. What will now help us to know that it's actually homogeneous? We check the degree here. This is power 2, this is power 2, this is x times 1, x raised to power 1, y raised to power 1, add the powers, 1 plus 1 will give you 2. So this xy term is also degree 2. Now degree 2 is common to these 3 terms here, which therefore means that the dx part is also what? Degree 2, which is the same as the degree of the dy part. So this is actually what? Homogeneous. So what we do, we're going to rewrite this equation as dy dx, which is the same as y prime equal to y squared plus xy minus x squared all over x squared. You know, I divided through by x squared. Quickly apply the transformation u is equal to x, differentiate it, and then you get u prime x plus what? U. And then you substitute. Is that it, sir? So let's do the substitution. Dy dx, which is our y prime, we're going to put u prime x plus u equal to, in place of this y squared, I'm going to put u squared x squared. Then here is going to be x. Now let's do that quickly, okay? We didn't have the time here. So we're going to do that. This is x, this is y, and y is ux. So you know it's going to be x times this x times u, which will give us x squared u. So I have x squared u, then minus x squared all over x squared. Then this is going to give us u prime x plus u equal to, did you take note that in the numerator, x squared is common to all the terms there, so you can factorize the x squared. And if that x squared is factorized from there, look at it, x squared, x squared, x squared. If you factorize it out, it's going to divide this x squared in the denominator. So you'll be left with u squared in the numerator plus u minus 1 here, all over 1. Of course, the x squared has cancelled out already. So walk through that. Now, move this u to the other side of the equation. So we're going to have u prime x equal to u squared. Now watch. If I transfer this u to this side of the equation, it's coming here as minus u. Is that not so? That minus u there plus this u will disappear to 0, and so you'll be left with u squared minus 1. Once again, check through it yourself. So do you see that this is a separable variable equation now? This is our separable what? Variable equation. You want to see that? Let's work it out and see. This is x times du over dx equal to u squared minus 1. If you cross multiply, you have x du equal to u squared minus 1 dx. And of course, we can now separate the variable. Take this x term to come to its controlling differential coefficient, the parent dx. Move u squared minus 1, the u variable, to its parent du. If that happens, you're going to have 1 over u squared minus 1 du equal to 1 over x dx. And you have separated the variable. All that is left is to integrate. Now to integrate this part, you're going to use integration by partial fraction. This is a standard integral in x, so we don't have problems here. We're going to take a break. When we come back, we will proceed in resolving this integration by solving this partial fraction first. Before the break, we obtained this separable variable form of this homogeneous equation. Is that okay? So we're now going to integrate this term. This is a standard integral already in x, we don't have problem there. And then this can be resolved into partial fraction because this denominator can factorize. Let's look at it. It's the same as 1 over, it's difference of 2 squares. So it's going to be u minus 1, and then u plus 1 du equal to, this is ln x already. I am not going to put plus c, the constant of integration, because I am not done integrating yet. Now this term is equivalent to this partial fraction because of this denominator, a over u minus 1 plus b over u plus 1. Okay, so we are now going to solve for a and b. To solve for a and b, we are going to use the denominator closing format. Looking at this denominator, if I let u to be equal to 1, this denominator of a will be what? 0. So let u be equal to 1, then this will be what? 0. It will allow me now to get a from here, okay? So a is equal to, let's come over here and cover the denominator of a from it, which is u minus 1. Alright, if I cover it, substitute u equal to 1 in what is left here. This is 1 over 1 plus 1, so a is equal to 1 over what? 2. Do same for b. Now let the denominator of b be equal to 0, and to do that, u will be equal to minus 1. Is that so? So let u be equal to minus 1. If you do that, it will allow you to get b. So b will now be equal to, go to this term again, close the denominator of b, which is u plus 1. If I close this u plus 1, you'll be left with 1 over u minus 1. then substitute minus 1 for what? For u. Look at it. If you do that, minus 1 here will give us 1 over minus 2. Is that okay? So the value of b quickly is minus 1 over 2. Now that we've gotten our a and b, we can now substitute into the partial fraction term here, and then we'll get integral. In place of a, what do you fix? 1 over 2. So that is going to be 1 over 2 open bracket u minus 1. You know that mathematically this over 2 will come down to multiply this u minus 1. Alright, du integral again this term. Or if you don't want to put the u here, you can just walk straight ahead. This plus will change to minus because of this minus 1 over 2 here. B is minus 1 over 2. That minus will change this plus to minus. So you have 1 over 2 open bracket u plus 1. Then du. Alright? Every term equal to ln x. We can now at this point integrate. You bring out integral 1 over 2 bracket u minus 1 will give us 1 over 2. You pull out that 1 over 2, which is a constant, you'll be left with 1 over u minus 1. Okay, which is going to give you ln of the denominator, because if you differentiate u minus 1, you will get 1, which is in the numerator. Then you move on again, the same thing will apply here. You have 1 over 2 ln u plus 1. And everything will be equal to ln x plus, you introduce your constant now, ln c. And so from here, I will clear fraction here. If I clear fraction is to multiply through by the LCM, which is 2. That's going to give us ln u minus 1 minus ln u plus 1. Then equal to, this will give us ln x plus ln, okay, 2 ln x plus ln c. Take note that if the LCM 2 multiplies this, you have 2 ln x. If that 2 multiplies this ln c, you are going to still get ln c, because constant times the constant of integration will still give you that constant of integration. Let's apply laws of logarithm here. Ln of this term minus ln of this term. You pick one of the lns, then you divide the numbers in this way. And that will be equal to power law of logarithm applied here, and then addition law of logarithm will give us, pick one of the ln, then you have a cx squared. Okay, you know what I did here, right? This term first will change to ln x raised to the power 2. Then that ln x raised to the power 2 plus ln c, you apply addition law of logarithm. Just pick one of the lns and then multiply c by x squared. Take exponential of both sides. If you do that, the ln will disappear. You'll be left with u minus 1 over u plus 1 equal to cx squared. We can now substitute for u, which you know is the same as y over what? X. Minus 1 all over y over x plus 1 equal to cx squared. If you simplify the numerator here by finding the LCM and working it out, you are going to get y minus x all over y plus x. You can work that out yourself and see. When you do that, the denominator x in the numerator will cancel the denominator x in the denominator here. Everything equal to cx squared. Now, recall that we were asked to obtain the IVP of this. I can leave this as the general solution of this problem. Now, to get the IVP simply means I have to substitute x equal to 1 for x here and y equal to 2 for y here, then calculate c. We are going to take a break. Once again, when we come back, we'll obtain the particular solution using the IVP given to us. Alright, now we now want to obtain the IVP value of this general solution. Is that okay? We want to obtain the IVP using this condition given to us. So we'll move on here. Y of 1 is equal to 2. Implies that x is equal to 1 and y is equal to 2. That's the meaning of that, okay? So we're going to come into this general solution. I'm fixing x equal to 1 and y equal to 2. So we'll come over here. This is 2 minus 1 all over. This is going to give us 2 plus 1 equal to c times 1 raised to power 2. So the numerator will give us 1 over 3 equal to c. Now you see clearly that the constant of integration here is equal to what? C. Therefore, our particular solution, otherwise you can say the IVP problem, is that okay? Is equal to, you now go back to the general solution. Is that okay? Go back to the general solution. Wherever you see your constant of integration, you fix in 1 over 3. So let us do that and see y minus x all over y plus x is equal to, in place of c, I'll fix in 1 over 3 x squared. And this becomes the solution to this problem. That is the MVP solution, alright? We call this solution the particular solution because we've been able to specify the value of this constant c. One can simplify this further in any form that the person prefers. Of course, depending on the option you see, you can still play around this. Now I can resolve this more as cross multiply. It's going to be 3 bracket y minus x. This times this, then equal to this times this, which is x squared bracket y plus x. If you feel like opening up the bracket and doing any further work, the choice is yours, okay? I'm going to stop at this point. Now, I would like you to work on this. Verify that y is equal to x bracket 1 plus cx squared all over 1 minus cx squared. That is to say that this general solution, is that okay? Verify that it's still equal to this. Because if I chose to say that, okay, this is the general solution, no argument, but in an option, I decide not to give you this. And maybe in the option you see something like this. How sure are you that this solution and this are the same? So verify this from this general solution. Is that okay? Meanwhile, don't forget, for this problem, we are looking for the particular solution which I've obtained and decided to stop at this point.